Week 2, Lesson 7, Modified Goodman and Soderberg. Last lesson we built the endurance limit. The stress a part survives forever under fully reverse loading. But most real parts never see fully reversed stress. They carry a steady mean stress with an alternating stress riding on top. This lesson combines those two against the endurance limit to produce a fatigue factor of safety, and it closes the two-lesson fatigue pair by finishing the same shaft we started in Lesson 6. Here's the problem. Same machined steel shaft from last lesson. We already derated its endurance limit to 212 megapascals. Now put it in service, where the bending stress isn't fully reversed. It swings from a tension peak down to a smaller compression. Given the ultimate and yield strengths, find the fatigue factor of safety two ways, modified Goodman and Soderberg. Then check separately that the first load cycle doesn't yield it. Concept 1. Real loading fluctuates. Instead of swinging symmetrically about zero, a real stress cycles between some maximum and minimum. Split that into two pieces, the mean, which is the average of the two, and the alternating amplitude, which is half the range. The alternating part is what grows the fatigue crack. The mean part shifts how damaging that swing is, and a tensile mean makes things worse. Fully reverse loading from last lesson is just the case where the mean is zero. Concept 2. The Goodman diagram. Put the alternating stress on the vertical axis and the mean stress on the horizontal. Each failure criterion is a straight line from the endurance limit on the alternating axis down to a strength on the mean axis. The ultimate for Goodman, the yield for Soderberg. Because yield is the smaller intercept, the Soderberg line sits inside the Goodman line. Anything Soderberg clears, Goodman clears too. A load point plotted inside a line is safe by that line. A third, separate yield line guards the first cycle. Concept 3. Three criteria on two strengths. Modified Goodman sums the alternating stress over the endurance limit plus the mean stress over the ultimate. Reach 1, and fatigue fails. Soderberg is identical, but divides the mean by the yield strength instead, a smaller number, so it's the more conservative line. And neither fatigue check catches first cycle yielding, so a separate yield check compares the peak stress against the yield strength. Near the yield corner, a part can pass Goodman and still yield, which is why both always run together. Setup. Turn stresses into factors of safety. First, resolve the cycle into its alternating and mean parts. Then the factor of safety is simply 1 over the interaction sum for each criterion. Goodman with the ultimate in the denominator, Soderberg with the yield. It answers how much you could scale the load before the point touches the line. The yield factor of safety is separate, the yield strength over the peak stress. Report both margins. Solve. Part 1. Resolve the cycle. Carry the endurance limit forward from Lesson 6 and take the ultimate and yield strengths as given. The alternating stress is half the range, and the trap is subtracting a negative minimum, which widens the range. The mean is the average of the peak and valley, positive here, so the average stress is tensile. That plots as our load point on the diagram. Solve Part 2. Three factors of safety. Both fatigue sums share the same alternating term, only the mean term changes with the denominator. Goodman lands at 1.50, Soderberg at 1.35, tighter because it divides the mean by the smaller yield strength. The yield check gives 1.89. All three clear 1, so the shaft is safe on every count, and Soderberg is the conservative margin to design to. Solve. Part 3. The Goodman equivalent stress. This folds the mean stress into a single equivalent fully reversed amplitude. The swing a mean free cycle would need to do the same fatigue damage. You can lay it straight onto an SN curve or compare it to the endurance limit. Ours comes out below the endurance limit, which lines up with the part passing Goodman. Treat it as a comparison tool, not a fourth factor of safety. Traps. 5 ways this setup bites. 1. The alternating stress is half the range and always positive, and subtracting a negative minimum widens it. 2. The mean can be negative. Don't force it positive. Fully reversed is just a zero mean. 3. Don't swap the strengths. Goodman uses the ultimate, Soderberg the yield, and mixing them flips which is conservative. 4. Never skip the yield check. Fatigue and yield are separate lines, and a part can pass one but not the other. 5. Feed the modified endurance limit from Lesson 6, never the raw polished specimen value. Quick recall. Resolve the cycle into mean and alternating. Run both fatigue criteria, Goodman on the ultimate, Soderberg on the yield, and a separate yield check on the peak stress. The factor of safety is 1 over each interaction sum. For variable amplitude loading, accumulate the damage with Miner's rule. Designed to the smallest margin, which here is Soderberg. Next up, Lesson 8, Thermal Stress and Strain. This lesson closed the fatigue pair. We built the endurance limit last time and combined mean and alternating stress against it here. Lesson 8 looks at the stress a part develops purely from a temperature change when it's constrained from expanding. No external load needed, yet a modest temperature swing in a restrained member can rival the mechanical stresses. Everything's at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.